we are going to the next objective, second objective of process control, and that is ensuring the stability of a process. So what do you mean by stability? You can see over here you have some variable. It gets some perturbation, some disturbance, something happens that it deviates from its set point on other side, and then it may oscillate for some time, but ultimately it settles down to the same point, to the same point, nearly to the same point from where it started. Then the system is said to be stable. So for bounded input, you get bounded output. The system is stable. This is what is the graphical representation of a stable system. Now, on the other hand, if we go to this point again, where the disturbance either makes the variable go up and up and up, never to come back, or it is going down and down and down, again never going to come back, or if at all it is going up and coming back, it is oscillating, but it's oscillating with ever increasing amplitude, like in this case. So in all the three cases, we say the system is unstable. So for the unbounded input, for the bounded input, the system is going out of bounds, either on the positive side or on the negative side. The impulse was the same, the disturbance was the same, but in this case, the system is going out of bounds. So we say the system is unstable. This is just revision of the concept, which I think you must have studied over a number of times till now. We come to the point where we have this time something called CSTR. CSTR stands for continuously stirred tank reactor. What is called continuously stirred tank reactor? For the one very simple reason. The reason is that you have a stirrer over here. This stirrer is just it's stirring, it's churning, it's blending the mixture over here. It is, as we had seen earlier, it was continuously stirred tank heater. In this case, it is not a heater, it's a reactor. It's a reactor in the sense that you have more than one stream getting into. So you have more than one stream getting into those two, three, four, whatsoever are the inputs going to this continuously stirred tank reactor. Those are the reactants. So A plus B giving C plus D kind of stuff. And the output is going out. Whatsoever is the output, it's coming over here. It's a product. So this product can be a simple product. This product can be a mixture of products. So if at all it is a simple product A, it's only A, or whatsoever is the output, then whatsoever is the concentration of this, whatsoever is the temperature of this, whatsoever is the flow rate of this is going out from here. It's only one stream. It is only one stream. Here you have number of streams, number of pipes. Each is carrying a different temperature, each is carrying a different flow rate, each is carrying a different concentration of the reactants. So although diagrammatically you see only one pipe going in, but practically or physically they can be 2, 3, 4, as many number, you can say I number of pipes where the reactants are flowing in, the reaction is taking place. And in this case, in this particular case, we are assuming that the reaction is exothermic. Exothermic means some heat is released. To remove the heat, what we do is we put this entire stirrer, entire stirred tank, you can say, in a jacket. This is the outer jacket, and we make some coolant flow in this jacket. So what is happening? Some flow rate of coolant, FC, is going in, and since there is no accumulation of any coolant in the jacket, the same amount of flow or the same flow rate should get out from this jacket. So this FC, as you can see over here, is same as this FC as you have over here, but the temperature of this coolant is CI, because its I is for input, and this temperature is O, temperature of the coolant O. O is here for output. So you can see something is going in and something is going out. It's same as you had something coming in and in, the flow rate is in and the temperature is in, and the concentration of the reactant coming through one pipe or two pipes or three pipes whatsoever. Again, for the sake of simplicity, we are assuming this pipe to a single pipe. For the time being, we're supposing it to be a single pipe, and the concentration of a particular constituent is moles, you can say, per unit volume, is the concentration of the input. The input is CAI, temperature of the input is TI, the flow rate is FI. Even if we assume this entire thing to be coming through a single pipe, even if it's coming through a single pipe, it's one reactant coming through a single pipe for the sake of simplicity, and this I denotes the input. Similarly here, this TCI denotes the temperature of the coolant of the input, and TCO denotes for temperature of the coolant of the output. So what you're going to see over here, if you're going to go ultimately for the dynamics of this, or the modeling of this, or the mathematics, in simple words, the mathematics of this entire process. So what you see over here is that you have something coming in the tank, something going outside the tank, something going in the cooling jacket, something going out from the cooling jacket, and the variables are, as you can see, the temperature of the coolant, the flow of the coolant. This happens to be the same as flow of the coolant over here because there is no accumulation, and this temperature can be different, has to be different, has to be higher, because it is extracting the heat, it's cooling the mixture over here. But as you see that this flow rate is not same as this flow rate, because this level can go up, this level can go down, and accordingly these flow rates, the inflow and the outflow, they can be different. Normally they are different. And similarly, the temperature of the reactant going in and the temperature of the reactant coming out, that also has to be different, because it's a reactant, and some reaction is taking place and exothermic reaction is taking place, and because the exothermic reaction is taking place, therefore the temperature can go up. Normally it goes up and it's brought down by the cooling jacket. So this is in journal I have explained in short, because this is your first exposure to CSTR, that is continuously stirred tank reactor. So this we will be referring to number of times in future also, and the same figure will be repeated number of times. And so I will not be repeating the explanation again and again. So I think you can, if at all you want to recall, you can play this video once again and revise whatsoever I have told you right now. Now, what is happening in this case? There are two things which are happening. Number one, if we see the amount of heat which is absorbed by the coolant and amount of heat which is released due to the reaction, these are two different things. You see, you have one, first of all, the heat released by the mixture when it's undergoing reaction. It's normally taking place in the presence of some catalyst. This heat released is following this curve. This heat released is following this curve, and this curve is S shaped curve. As you can see from the shape, it is called sigmoidal shape. It's a sigmoidal shaped curve. And as we see, as the temperature of the tank, it changes with respect to time, the heat released is also changing, because as the temperature goes high, the catalyst becomes more active and the reaction becomes more active, and thereby it leads to higher release of energy. So this is the way it is going to change. Now, the heat which is absorbed actually at a given flow rate, it's again very important, at a given flow rate. Now as the temperature it increases, the difference between the coolant and the mixture, that also goes on increasing, because let us say coolant is flowing at a 4 degree Celsius and the mixture is varying anywhere from 30 degree to 70 degree. So as the temperature becomes higher and higher and higher, the difference becomes higher. And so as per the Newton's law of cooling, if you remember, the amount of heat extracted is directly proportional to temperature for a given flow rate. It's for a given flow rate. I'm repeating again and again, because if I change the flow rate, then the slope of this may also change, and I don't want to discuss that thing at this moment of time. So I'm keeping the flow rate of the coolant as fixed. So at this stage, we see that this straight line is the amount of heat which is absorbed by the coolant, and this sigmoidal curve is the amount of heat which is released. This is how they're going to change with respect to temperature. This is how they're going to change with respect to temperature. And we see that there are 3 points. This is a point P1, and you have point P2, and you have point P3. These are the 3 points which are at the state where you achieve some equilibrium. Equilibrium means that at this point the heat released is equal to heat absorbed. So an equilibrium is reached. Similarly, at this point heat released is equal to heat absorbed. So another point of equilibrium is established, and over here again heat released is equal to heat absorbed, and so you have the third point of equilibrium taking place at this point. But we have to see whether these equilibrium are stable equilibriums or unstable equilibrium or neutral equilibrium. What kind of equilibrium is there, we have to see. So we can right now see at what happens at P1, what happens at P2, and what happens at P3. So let us start from let us say uh, P2, okay, because it's the center. Let's see what happens at P2. Just listen to me very carefully. We will show these things in graphs again. At P2 the temperature is T2, and let us say the temperature of this entire system, it goes from T2 to T2 dash. For some reason some disturbance happens and it changes from P2 to, instead of going in from T2, it goes to T2 dash. It goes slightly higher. The moment it becomes slightly higher, see very carefully. The moment it becomes slightly higher, at this temperature the heat produced is higher and the heat extracted is lower. At this point T2 dash, the heat produced will be Q2 dash, this much, and the heat absorbed will be Q2 double dash at this point. So friends, what do you see? That the moment temperature increases from T2 to T2 dash, the heat produced is more and heat absorbed is less, and this is going to result in the temperature going still higher. It's the temperature will still become higher, because you know the released is more, absorbed is less, temperature will become higher and higher and higher. This will show in graph. It means that it will never come back to P2, right? What about if it goes slightly less? If it comes to this point, then in this particular case, the heat absorbed is higher and the heat released at this temperature will be lower. If the temperature goes lower, then the heat absorbed is higher and the heat released is lower, means the temperature will go further low and further low. It will never come back to P2. So we see that as long as it is exactly at P2, the system is in equilibrium, it will remain so. But the moment there is slight disturbance on the higher side, the temperature will continue to move up and up and up. And where will it settle? Ultimately, it's going to settle only at temperature T3. At T3, it's going to settle. We will see how it settles at T3 graphically also. But right now, it's not going to stop till point P3 is achieved, where again the temperature of the heat released becomes equal to heat absorbed. And while going down, once it goes down, it continues to go down and down and down and down, and ultimately it will reach at point P1 where it's going to stabilize. We'll see how it stabilizes, and that's the point where you see the point P1. Here again, the temperature is at T1 and the heat released is equal to heat absorbed. So friends, once it moves from P2 to either P3 or P2, this is what we have seen, that as long as it is P2, good, but there's a slight change, and because of that, if it is left unattended, if we don't change the flow rate or don't do anything, then what is going to happen? It's going to settle only at P3. And if it is going down, for some reason it goes down, then it is going to settle only at P1. Now let us see once again whether it is going to actually stabilize at P3 or not. What happens at P3? What if the temperature becomes higher? The temperature becomes higher, heat absorbed is more, and at this point heat released is less. Because heat absorbed is more, heat released is less, the temperature will again come back to T3. And suppose for some reason the temperature becomes lesser than T3, then at what happens at this point? Because the temperature is lesser than T3, here the heat released is more, as you can see, and the heat absorbed is less at this point, right? And therefore the temperature is again going to come back to T3. So it's some way it's going to stabilize itself at T3. Even if there is a change, it's to come back to T3. In this side also it's going to come back to T3. It was not so in case of P2. If the temperature increases, it continues to increase and settles only at T3. If it is decreasing, it continues to decrease and it settles only at T1. Let us say whether it settles at T1 or not. We can see it's at temperature T1. I think you can very well see over here. You can pause the video and think also. At T1, what happens is that suppose there is increase in temperature. So temperature increases as you move along this axis, temperature increases and temperature becomes this much. At this temperature, what is the heat released? Heat released is, this is the case of heat released is at this much point, and heat absorbed is here more. Heat absorbed is more and heat released is less, and so the temperature will again fall down to T1. And same is the case, you can say, and vice versa. If it goes down, then again you can see if it comes over here, then heat released is more and heat absorbed is less, so it's again going to come back at T1. So at T1 the system is in stable equilibrium. At T3 the system is in stable equilibrium, and at T2 the system is in unstable equilibrium, right? This is what you're going to see in the coming slides graphically. But before that, you may would like to know that if it is stable at T1 or if it is stable at T3, then we should operate the system at either T1 or at T3. But the process requirement is that we should operate at T2. Even if it is unstable, the process requirement is that we should operate at T2. Why? Because at T1, I will repeat this later again, at T1 the temperature is low and the yield is less. At low temperature the yield of the reactant giving the product is less. And at T3 the temperature is high, so the catalyst can get destroyed or the system can damage itself, so the system is not very comfortable at T3. So we cannot operate at T3 because it can damage the system. We cannot operate at T1 because it can somehow lead to lower yields. We have to operate at P2. The problem is that at P2 the system is inherently unstable. It is inherently unstable, so it needs to be stabilized. How it needs to be stabilized? We have to use some controllers. So this is the second objective. The system is inherently unstable, but we need to have some controller. So that controller is going to control the system. It's just like riding a bicycle. If we just push a bicycle, it will either fall on the left or fall on the right. It will not remain. It is inherently unstable. But then we put a rider on it, a skilled rider on it. That rider will become a controller, and that is going to balance the bicycle at the vertical position. Inherently it is unstable, but it's going to stabilize it by putting a balance. Similarly, the system is inherently unstable at P2, but for the reasons I have already told you and for the reasons I will be repeating again, this needs to be stabilized, and this is the second objective of process control or process controller, ensuring the stability of a process which is inherently unstable, but we need to stabilize it. This is what I have already told you, and you have already seen that the temperature is at P2. If it goes to T2 dash, then the temperature will continue to rise and stabilize only at T3. On the other hand, if for some reason it is going down, it will continue to go down and stabilize only at T1. This is what I had explained. This is what you can see in the graphical manner. Similarly, at T3, if you see at T3, if the temperature goes slightly up, right, then it's going to come down, and ultimately because of inertia it may undershoot, but it's going to stabilize at T3. So at T3 the system is quite stable. Similarly at T1, as you can see over here, again if it slightly goes up, then again it's going to come down, and because of inertia, even if it overshoots a little, then again it's restoring temperature, and ultimately it's going to settle down at T1 also. So what we see graphically is that T1 and T3 are inherently stable points, and P2 is inherently unstable point. Friends, let's conclude. I'm going to repeat these things for the final time, and I'm going to like to just read it out verbatim, word by word, so that the things are very clear. Sometimes you would like to operate this CSTR, that is continuously stirred tank reactor, at the middle point, but at the middle point the system is quite unstable. So this is for the following reasons. Why do we want to operate it at the middle point although it is unstable? Because if you operate at P1, the temperature is low and the yields are low. If you operate at P3, the temperature is high, and therefore it can damage the product, or it can damage the catalyst. So in such case, we need a controller that will ensure the stability of the operation at the middle steady state point, and the middle steady state point we know is inherently unstable. So you think of a mechanism, or I think of a mechanism to stabilize the operation of the reactor at the unstable steady state P2. So what kind of react controller you want? Some kind of feedback controller we will discuss. We have plenty of lectures left, and that's what you're going to do to study the control mechanisms to ensure the stability of a process. Friends, in case you have any queries or doubts or any observations or comments, you can always contact me through Zoom or WhatsApp, or make phone call or face-to-face interaction as the case may be. I thank you for being with me, and I hope you have a safe stay. Enjoy learning. Bye bye.